Okay, 12.7. I could call it 12.7b. How about that's a good name for it? 12.7b, the collision model Arrhenius equation. Well, I don't know why I'm writing it. I just told you. But 7b, Arrhenius equation. It's in 12.7, but there's another reason for this too. This is something that was on the AP. It's been on the AP before in past years. And recently they said they would discontinue like showing that so much now that this is not, that equation is no longer on the well, actually it was never on the formula sheet. I don't believe it was either. No, it wasn't. I don't think it was. So this is interesting. Well, this is not a long thing. It's something I want you to know in the class. And as I've told you before, a long time ago they used to always put the real gas equation on the AP formula sheet. All right, they called it the van der Waals equation, the PV and RT with the N minus NB and all that. Well, then they quit putting it many years. People thought, oh, they're not going to ask about it. And then one year they asked a question about it, but what they did was, in the top of the FRQ question, they gave you that equation. So, you know, I guess there could be an off chance that they could show you, I misspelled, the Arrhenius equation. They could give you this equation, and so that's why I want to go over it. Okay, now, in the notes, I have to use my notes here, as I told you. I think I get more ink for this. Okay, this is in 12.7. You skip down to this page. Actually, I didn't actually number the page. But the last thing we did here was about the Maxwell-Boltzmann distribution. And I was telling you how that works. How activation energy can be put onto a Maxwell-Boltzmann distribution. Well, that's a good beginning to this, because that's what Arrhenius investigated, was how can you calculate how can you calculate the activation energy? So, first, it's an interesting question it talked about here. It just mentioned here's a little question there. What would be the correct, which two of these would be a correct collision that could result in giving you the intermediate or the activated complex? And in this case, it would be, if you want to read that question, it's kind of a review of what we talked about. But it would be the first one, the O. This one could do it, okay? Oh, you can't really see that on that screen, can you? Does it work? Oh, no, that messes things up. This one has it. And also it would be, where do you have an O2 coming together? Oh, those right there. The O2s could hit together on that side as well. Yeah, the very last one. ONBR, NO. Let me see that for a minute. The two BRs hitting, they could make BR2. Oh, no, I think it would be that, not the second, third, 1, 2, 3, 4. I'm just looking at that myself. Which two can result in forming BR2? Well, it would be, BR2. Yeah, it would be that one. That one and the first one. Those two. Because those are going to form BR. And if those form BR2, then of course the NO and NO are already released. There they could also do it because the BRs can form together. But anywhere else, I can't see it happening. Yeah. Okay. Now, all right. Well, that's a summary of the last section there. I didn't see that before I went over. I would have probably talked about it in the last video. Arrhenius equation. Now, guess what? You don't really have to know. Well, you don't have to know this at all. I told you the Arrhenius equation was never given on anything. That's the official Arrhenius equation. Like, what in the world? You can relate K to these different variables. A is something called what does it say there? The frequency factor. You don't even have to worry about that. I'm going to show you why. But what you do is you take this equation and then you take the natural log of both sides of the equation. And when you take the natural log of both sides, you end up getting this form. Okay, so 12.7b. The next page shows you ln of k. The natural log of k is equal to negative EA over R times 1 over T plus ln A. Now, A is something called the frequency factor. Has to do with collisions. And you're not going to even have to really worry about that. But when they used to give you this equation, here's the only thing you really need to know about this. The only thing about this that's important is, guess what? This equation is in the form of y equals mx plus b. Aha! When you graph it. Does this look a little bit familiar? So what does that mean? That means that negative EA over R is equal to the slope. And technically we should make it negative. That way negative is negative. What is EA? EA is the activation energy. So what I would say is, and I'll give you this equation, you know, or you'll have it. You have it now. I would, if I saw that equation written down, or if it was on an FRQ at the top, I would do this. I'd say, okay, and I'd write that below it. That slope, that's y, and then x is 1 over t. Another thing you need to know is that temperature, that's temperature, and it must be K. It must be in Kelvin. The inverse of the Kelvin temperature is here. EA is in joules, the activation energy. Wow, am I getting, I was thinking my screen was getting weird color or whatever. Maybe I just look real yellowish. It just feels yellow with all this. All right, that's the activation energy. R, guess what? R is the gas constant from PV and RT. However, when you see the AP exam, they're going to give you a sheet that says R equals 0.0821 liter atmosphere mole Kelvin. But you're also going to see 8.314 moles joules Kelvin. Mole and joule Kelvin. Or actually, it's joules mole. I'm sorry. It's joules per mole Kelvin. Sorry about that. I had it backwards. All right. And there's another one too. So there's another way to write R. The reason it has to do with physics, actually, with work, what's called work and energy. Work and energy can both be measured in joules, okay? Well, it turns out on PV and RT, P times V, which is pressure times volume, atmospheres times liters. Liter atmosphere is a way to measure work and energy, believe it or not. All right, liter atmosphere. That seems kind of a strange thing. You got to look at physics to figure that out, to know why. You don't have to worry about it. But liter atmosphere measures work. Joules measures work. Calories measures work also. Calories is the English imperial, U.S. system that we use from England, Britain, is calories. We would measure energy and work in calories. But in the metric system, they use joules to measure work and energy. But liter atmosphere can also measure work. But the important thing to know is, when you see joule, think energy. Anytime you're doing any calculation, anywhere in any chapter, it's going to come back in later on. Anytime there's something about energy or electricity, and you'll find that out later, electrical voltage, it's always going to be this 8.314. You're not going to use the other. And since we're trying to find activation energy, the R value will be the 8.314 value. It's the same number. It's just been converted according to physics units. It's like the physics conversion stuff I showed you. All right. So what's the big deal about it? Let me explain about this first here. Sorry. All right. Arrhenius. We got a little picture of him somewhere. I'll have to flip back a little bit. Svante Arrhenius. There he is right there. And you're going to hear about him when we get into the acid-base chapter, because he also did a definition of acids. Okay? But all I'll tell you is he with this equation, he correlated how does the activation energy, how can you calculate the activation energy based on K and vice versa. If I know K, what's the activation energy? Or if I know activation energy, what is K at a given temperature? Remember, K is only true at a given temp. So, I think I showed you in the earlier, let me see, where was that? It was on the first page. If you ever graphed K versus temperature, you would get a curve, exponential curve. Yeah, there it is. K versus temperature gives you a curve like this. Temperature, I'll put K in Kelvin. But now, if you were to graph, watch this, the natural log of K, same data. So say I gave you all this data. Here's K, here's the temperature, and we go all the way down. Oh, actually, it'll be the other way around. Here's the temperature, and here's the K. Temperature in Kelvin, okay? Here's the temperature, here's the K. X, Y. If I graph that, 1 over... If I graph that, I'm not going to see anything. I'll just have the way I just showed you a moment ago. All right? K versus temperature is going to give you that curve, okay? But if you take the natural log of that, the inverse of temperature and the natural log of K, guess what happens? You get a straight line, but with a negative slope. And that negative gives it away right there. Let me see what page. Did I draw it for you? Or do I have to draw it for you now? No, I didn't. I didn't show you that. But you're going to get a straight line with a negative slope. If you graph K versus, the natural log of K versus 1 over the temperature of Kelvin. What a crazy looking... That, you need to know that. What I drew before, I know I put the curve and then I put, I did it, but I didn't say it. All right, I should have drawn 2 graphs. That's what I should have done. If I graph K meaning the constant times temperature versus temperature Kelvin, I get the curve. But if I take natural log of K and I do the inverse of the temp, now I get a straight line going down. Now here's why it matters. The slope of this line, if I take any 2 points on the line, the slope of that line will equal the activation energy divided by R. This is all you need to know. It's a calculation. I'm going to do one calculation problem for you and let you do one. And you know, this used to be a bigger deal. And on the worksheet I'm going to give you, you only have to do number 2A and B. I don't know if I said that in the very beginning. Only 2A, one problem, kind of like what I'm doing here. But I spent a lot of time making it. On the back, number 3 is a great problem where you actually graph and do it yourself and all that. But oh well, we're not gonna worry too much about the time doing that one. Okay, so I'm going to do example A, and it says, and what I'll do also, just to give me more space, I'll take this out. I guess I like to remember y equals negative mx plus negative mx plus b. I like to remember that just to see, just because it'll help me, you know, if I saw a graph. Okay. The following reaction was carried out at different temperatures. The following K values were obtained. So you have N2O5, 2 N2O5 giving you NO2 and O2. All right, 4 NO2 plus O2. Oh yeah, I can do it this way too. Here it is, the notes. And they gave you all these values for K and all these values for temperature. Now, determine the activation energy for this reaction, explain, and then refer to the data on the next page. Oh, I made this easy for you. Now, when you do it, it's going to be a little bit tougher. But let me tell you what you need to do. It says explain it. Here's what has to be done. K and temp aren't going to help me if I graph those out. But if I take the natural log of all 5 of those values, Ln of all those, I can write it right there. Natural log of K, put it there. And for the temperature, I got to do 2 things. First, I got to change it to Kelvin. Can you remember how I get to Kelvin? You add 273.15 plus the Celsius. So I'm going to change all of these. I'll pick another column, put temperature Kelvin. Then another column, 1 over temperature Kelvin. So I've got to have LNK column, and I got to have 1 over temperature Kelvin. You could jump all the way to 1 over temp Kelvin if you want, but I would put a Kelvin than that. Okay, and when you do that, magically, it's done for you. Yay, there it is, and there's a line. So I did it. But when you have it on your calculator, you got to do it yourself. Now, as I told you, if you want to do number 3 for fun, you could do that. You could do that instead of number 2. Well, I would probably do number 2 and 3, whatever. But number 3 is a great one. But it'll make you do all this stuff. But you only need to do 2 points. When you do the homework I assigned for you, 2A and B, you can just do, I would just take the first and the last point. You only need to do 2 points to find the slope, okay? And that'll be good enough, all right? So you graph it out, and there's a line. You get a line, negative slope going down, okay? And again, temperature, Kelvin, inverse. You could put, I probably should have put TK to the negative 1, not K to the negative 1, but oh well. Oh well, 1 over Kelvin. I guess you could do that. Okay, but anyway, there's LNK there. And actually, I don't think I made this up. I think I got this from somewhere else. So that might be a criticism of something of the book. Maybe they know something I didn't. All right. Example. Oh, wait a minute. No, I better do this one. I better do example B. Example A. Well, anyway, all you do is you find the slope of the line and then you set it to EA over R, then solve for EA. But let me do the next one for you because this is exactly like the homework problem I gave you. It says a first order reaction has the rate constants of K is 4.6, 10 to the negative 2, S negative 1 at 0, and 8.1, 10 to the negative 2 at 20 Celsius. What's the value of the activation energy? This came out of, your book, and I put very involved math. So let's do some very involved math. Here we go. Example B. I should have just done the other one, shouldn't I? To not mess myself up. I could have gotten out of this a little bit, but oh well. Here we go. So we've got Kelvin. We got your K constants. One of them is 4.6, 10 to the negative 2. The other one, and it's at 0 Celsius. All right, and now we also have 8.1 times 10 to the negative 2, and it's going to be at 20 degrees Celsius. So, like I just showed you, what you should do first we're going to take the natural log of these two. So 4.6, 10 to the negative 2 is 0.0. All right, that number, Ln, is negative 3.0. In fact, let me do it this way. Ln of K, small lowercase k, is negative 3.08. Then 8.1 to the negative 2, natural log, is negative 2.51. Excuse me. Talk dust. Okay. Now, temperature. First, let's Kelvinize that baby. So Kelvinize this, and that means, 273.15. Just put 273 there. And then 20, we'll make that 293. That's easy enough to do. But now we got to put 1 over TK. So I get the inverse. So 1 divided by 273 is 3.67. 10 to the negative 3. And 293 inverse is 3.41. 10 to the negative 3. Okay. So what we have, even though, if I had to do a problem like this, I just tell students to do this too. You can just draw a little graph just to kind of remind yourself 1 over temp Kelvin, and that's the line you get. So here's one point, and then here's another point. And so it's Y2, find the slope. Slope is equal to negative K. It is a negative number, but we'll just, I'm sorry, not negative K, negative EA over R. But slope is going to be equal to Y2 minus Y1 over X2 minus X1. So here I go. Let's plug these numbers in right now. So X and Y, maybe I'll get another, I think I hurt I must have destroyed one of my orange chalk. I was going to use an orange chalk here. Oh wait, here's one. To put my X and Y. Okay, so your X-axis is 1 over temperature Kelvin. Aha. Your Y-axis is LNK. Aha. That's why I draw this, to make sure that it helps me to not make a goofy mistake. All right? So Y2 minus Y1 over X2 minus X1. So Y2 is negative 2.51 minus negative 3.08. Now X2 is, on this axis, 3.41 times 10 to the negative 3 minus 3.67 times 10 to the negative 3. All right, so 2.51 negative. Minus a negative is plus 3.08. So it's going to be 0.57 on the top. And the bottom, 3.41, 10 to the negative 3. Minus 3.67, 10 to the negative 3. Is 2.6, negative 2.6. Actually, negative 2.60. Oh, wait a minute. 2.6 to 10 to the negative 4. So that's 0.260. Yeah, that's right. It should have another sig fig. If you wanted to, you could expand it out and you do the box rule, but that'll work out correctly. And then what you do is divide that out. So 0.57 divided by 2.6, 10 to the negative 4. And I did something on my calculator wrong. 0.57 divided by 2.6, 10 to the negative 4. It's a negative 2190 with sig. Oh, only 2 sig figs. Actually, 2200. Negative 2200. Now, let me double check this math one more time. 2.51 negative plus 3.08, 0.57, and then divided by 2.6, 10 to the negative 4, and it's a negative though, 2190. Okay, I'm trusting my math. Since we're not in class, when we're in class, I rely on people to tell me, to do it along with me. And they say, oh, Vela, you got the... Okay, but I think I got all the math right. Okay, so this is the slope, negative 2200. So then what you do, and I guess I can actually fit it over here. So we know that the negative slope, well, how about this? Slope is equal to, negative, it is equal to negative EA over R. Since the slope is negative, so it's kind of like when you did K, the activation energy is always positive. I know I told you that in another video, so you just got to make sure it ends up being positive when you do your math. So since the slope is negative 2200, so if you did for example, if you subtracted these backwards, these two numbers, you might just, like a careless error, you get 2200. It doesn't matter. You just did something with the math. This number should come out to be negative. If you do your slope should come out to be negative. If you do, y2 minus y1 over x2 minus x1, assuming that you're, this is x1, y1, x2, y2. To take the later one, it should always be a negative slope. Okay, negative 2200 equals EA over, can you remember the R value is 8.314 joules per mole Kelvin. So that is equal to 8.314 joules per mole Kelvin. Okay, and then actually, though I didn't write this down, I'm not going to worry about it. Okay, it's going to end up being in joules. These are going to cancel out. Your answer is going to end up being in joules. Okay, so 2200 times 8.314, and that's a negative, by the way, so it's going to end up being positive now, is 18,182, or how about, 18000 with the sig figs equals EA. So that'd be joules. So that's 18 kilojoules. Okay, so 2200 times 8.314 is I get 1829.08, 18,290.8, which with sig figs will be just 18,000. Sorry, 18,000 is your activation energy. All right, that's how you do it. So just do number 2, A and B. And even though it's tedious math, but the thing is, you only have to do one problem. And look, that lesson video was only 24 minutes long. One of the shortest in this chapter. See you.